Okay guys, just going to look at radian measure, and to do that we're going to need a circle of any given radius, I want quadrants as well, so I'm just using the edge of the paper here to very quickly create orthogonal axis. Okay, from there I'm going to create a circle centered on the origin. Okay, just to remind ourselves of a few basic things. Just the standard position of angle is when the initial arm lies on the positive x-axis. So we typically open our angle up this way. Looking at a formula which has theta in it in radians, we can work backwards to find out the definition of theta. So L is the length of the arc. Arc is a part of a circle. So L is the length of the arc. Theta has this new mystical measure, radian, and the radius of the circle is r. Okay, so by definition, and by rearranging this formula here, you have that theta equals the length of the arc divided by the radius on any circle to describe the angle. So the angle and the arc are really one and the same thing. You can't separate one from the other once you're given a circle. Once you create an angle at the center, you create an arc. Okay, now just to look at what would 360 degrees be in radians, we could say, well, 360 degrees implies that the length is 2 pi r and the radius is r. So 360 degrees is the same as 2 pi. Dividing by 2, we get that 180 degrees equals pi. So you want to remember this, that pi is the angle is a straight angle. Okay. Now 180 degrees, if you don't have a very strong sense of number, and you haven't learned this off, you might want to go to your calculator and use number theory to factorize 180 degrees. Okay, so we see a square on 2, a square on 3 times 5. So 2 squared times 3 squared times 5. Okay. And there'll be much more about that later. So we'll often see things like pi over 15, pi over 6, pi over 3, pi over 9. And the reason we see them so often is basically that the factors, there are quite a lot of pairs of factors here. And it's no harm in breaking them out there like this. Taking 2 on its own, taking 4 on its own, taking 9 on its own, we get 20 degrees. And that continues. Interesting ones are 15 on its own. What happens when we get 15 on its own? That's 3 5s. Well, there's 3 4s, 12 degrees left. Okay, so that's a really interesting one. So example, if you want to know, hey, what's pi over 15? And the answer is 12 degrees. Okay. Now the conversion factor to go from degrees to radians is going to be pi over 180 degrees to go into radians. You multiply by that. And 180 degrees over pi to go into degrees, because this is essentially 1. So all you're doing is changing the unit measure. If I want to know what's 31 degrees in radians, I will go pi over 180 degrees, and the degrees cancel obviously, and just do the calculation and get it from there. Okay, so just to go through the theory of the circle, a segment is it's the part of the circle that gets cut off between a chord and the circle itself, the circumference of the circle itself. So that's called a segment. And that should remind you of a line segment. So if you cut off part of a line, you get a line segment. And if you cut off part of a circle, you get a circle segment. A sector is a kind of slice of pizza. It's got 3 edges, if you like. It's got 2 radiuses plus the length, whereas a segment has only 2 edges, a curved edge and a straight chord edge. Okay. So there is a lot of manipulate, or at least there's a lot of logical reasoning to coming up with formula for the length of an arc. If you do it in radians, it's really simple. You've got it here. But I just want to say one more thing. It's very important for students to understand why we would switch from degrees, which is time honored by certainly, into radians, which just seems so unreasonable because they have this pi. Generally speaking, if we're using special values like 45 degrees, 30 degrees, 60 degrees, and so on, then we end up with things like 60 degrees, for example, is equal to pi over 3. And you're going, this seems so unreasonable because pi is irrational. So surely we were doing great with our 360 degrees. And the reason is, the only best reason I can give you is the word calculus, which you'll be studying next year. So it's because with calculus, we're interested in the rate of change of things like our sine graph. And then it turns out the rate of change of our sine graph is equal to cos. Okay, which is fantastic. The slope of sine is equal to cos. So the slope there is 1 and the cos is 1. So that's a particularly convenient result. And so I'd say to you that you really only need to worry about radians mainly when you're doing calculus. And you have to be very careful not to slip back into degrees. Whereas when you're doing section 2.3 on trigonometry and the section on measurements and volumes and areas, even if they give you a question in terms of radians, you can always switch it back to degrees. So probably enough said there. Sorry, let me develop the segment. So the segment would be part of a circle, which is pi r squared. And you're asking, well, how much of that circle are we talking about? Well, it would be L over 2 pi r, if we're doing it in terms of radians. Okay. So L would be r theta. And then the pi's would cancel. One of the r's would cancel. Okay, and we get pi r squared. We get theta r squared over 2, which is this formula here. So half of r times theta squared is the area of the sector. Now that theta has to be in radians. We've just used it using the radian formula for the length of the arc, comparing the length of the arc with this full circle. So, and we don't just look up a formula. We want to make it our own and get to know it. Okay, so we want to be able to use it without having to look it up. So half the radius times t squared. So you square if you want to get the area, you square the angle, and you multiply it by half the radius. So this half of a radius becomes an important measurement. Okay. Now, and then everything else here is just proportional. They're all proportional, but these are just proportional in their own right, theta over 360. So just think of those in terms of proportions. But this new formula here is just very nice, and I think you should learn that. Okay, we're going to get down to doing some of the questions now from the from section 16.6, which I'll start on a new video.